starting with Guillaume Veylon, who is an engineer and PhD student in IRSTEA, the French National Institute of Environmental Sciences, and Guillaume will discuss the problem of micromechanically-based modeling and microstructural enrichment for soil liquefaction modeling. So Guillaume, try to check the timing, to fulfill the timing as close as possible.
Okay, and I have the difficult task to let you sleep after the lunch. Don't be too noisy. So I will talk about the micromechanically models and microstructural enrichments for soil liquefaction modeling. I will try to present the challenges and also present some results, some partial results we obtained, and to draw some perspectives. So I tried to stick to the topic of the workshop, which was the seismic driven risks. So my presentation will be based on the soil liquefaction mechanism, which is at the origin of major damages in civil engineering structures during an earthquake. It was more thoroughly brought to attention of engineers in 1964 when two earthquakes struck the planet, the Niigata and Alaska earthquake, and until recently soil liquefaction is still a major source of destructions. I read somewhere that in Kobe, during the Hanshin 1995 earthquake, the amount of reconstruction of what was destructed and mostly due to liquefaction was about $100 billion. So the phenomena associated to soil liquefaction can be the loss of bearing capacity, as you can see here in the case of a bridge, the sliding of natural or artificial slopes, the cracks or lateral spreading of embankments or dams. Here is an example taken during the Alaska earthquake. And there are also consequences in terms of settlements and sunboils, even on flat areas. So what is soil liquefaction? It is defined as the annulment of effective stress under undrained loading conditions. What is important in the undrained condition is that it appears under constant volume deformation. Here you have some kind of a scheme representing the effect of the mechanism of liquefaction during an earthquake. Before the earthquake, the granular material has a structure, often loose with anisotropy. And during the earthquake, the fact that the ground motion is very fast makes that the deformations of the soil is done at constant volume. And if the intensity of the earthquake is strong enough, the annulment of the effective stress can appear because the grains lose their contact with each other. And after the earthquake, the drainage of the soil layer induce consolidation of the granular material. So some laboratory experiments showed that the onset of liquefaction was highly dependent on soil microstructure. It has been highlighted using different sample preparation methods, and also by the study of the effect of rotation of principal stress directions in triaxial tests, undrained triaxial tests. So the modeling of soil liquefaction requires the description of soil microstructure and its evolution along the loading path. Several attempts are therefore being conducted in the context of macroscopic phenomenological constitutive models. But these models require additional parameters about the evolution of microstructural law, and these parameters has to be calibrated. Here you have the example of one and grow approach, which makes the rough assumption that the fabric, which is integrated in the expression of the dilatancy angle, evolves proportionally to the deviatoric stress ratio. So here, the problem we are trying to tackle is that we are trying to develop a fully multi-scale model which accounts for the microstructure and its evolution all along the loading in story without with making the least assumption as possible. The principle of multi-scale model, I won't present it because a lot of brilliant speakers did it this morning. So you know that it is based on localization and averaging schemes and description of the local behavior either at the contact scale or at the mesoscopic scales. The first model, which was developed by François in the early 2000s, was the micro-direction model, which postulated a distribution of pairs of grains in contact, and the local deformation at the contact zone was assumed to be proportional to the mean incremental stress tensor acting on the whole granular assembly. But of course, granular assembly, as shown by Niels, for example, and a lot of other authors, the granular assembly is essentially deformed due to grain rearrangement, and so the relative displacement depends on their local environment. So it is needed to introduce an intermediate mesoscopic scale, which enables to describe the local rearrangements of grains during the loading. Here you have a little figure explaining that at the macroscopic scale, of course, the deformation is equal to the macroscopic deformation. We know that this assumption is false at the scale of two grains in contact, so we are looking for a proper scale for which the proportionality between the macroscopic deformation and the mesoscopic deformation is fulfilled. So the idea of François was to integrate, to define a real mesoscopic scale, and to model the granular assembly as a distribution of oriented hexagonal grain pattern, like this. So each hexagon is assumed to remain symmetric. Initially it is symmetric, and it remains symmetric. There are two axes of symmetry on the principal direction and on the normal directions. And given that we assume that the external loading acting on this hexagon are symmetric, it remains symmetric all along the loading path. The deformation of any hexagon is also assumed to derive from the macroscopic strains, as noted here. And if we make a comparison with the approach of Bernard this morning, we have the same philosophy of searching the appropriate mesodomain. And here, each face would be each hexagon of the H micro-directional model. And in this model, what was the phenomenological model describing the behavior of the mesodomain is replaced by a micromechanically approach plus this kinematic assumption on the proportionality of the deformation with the macroscopic strains. So I will briefly present the model. So here we have the notations. Due to symmetry, we only have three unknown contact forces, N1, T1, and N2. And the geometry is perfectly defined by the branch vectors D1 and D2. For symmetry reason, these are the only unknown of the problem. It is possible to, writing the equilibrium of the grains, it is possible to determine the force, the external forces needed to ensure the equilibrium of the hexagon, and then finally to define a mesoscopic stress, as it is possible to define. And these mesoscopic stress do not depend on the contact regime. And after, once we determine the mesoscopic stress at the scale of the hexagon, by an homogenization scheme, it is possible to determine the whole, the scale, the stress tensor at the scale of the material points inside a given volume. So this hexagon, in order to stay hexagons, there are other constraints on their geometrical properties. So we do not allow them to interpenetrate between the grains, between the center grains, in both directions. So it is using these inequalities, it is possible to determine in the 3 dimensions the set of possible states of the hexagonal pattern. Here in the x-axis you have the opening angle alpha, which is which corresponds here to the opening angle, the difference of orientation between the axis N and this branch vector D1. That's it. And in z-axis and y-axis, there are the two stress, mesoscopic stress. In this, it can be seen on this equation that there is an infinite set of geometrical possible configurations for given states sigma 1 and sigma 2. Which means that it is possible to imagine that starting from an initial state here and following 2 different loading paths in the geometrical state space, it is possible to reach this 2 different points with the same stress state sigma 1 and sigma 2, but with different alpha configurations, and alpha being the microstructural parameter, what gives the microstructure to the hexagon. So the state of the granular assembly is uniquely defined only if we enrich the stress state with the microstructural parameter alpha. It is also possible to, of course, to derive the tangent stiffness matrix for this associated to the hexagon, and I will pass very quickly. But we write the incremental. The contact force increments in terms of elastic plastic model using the parameters Kn, Kt, and phi j, which are the normal stiffness, tangential stiffness, and intergranular friction angle. And Xi is a quantity corresponding to the sign of the direction of solicitation and compression or extension of the hexagon. It is possible to write the following algebraic formulation, which relates the deformation of the hexagon with the deformation of the branch of the geometrical configuration with increments, which are defined by D1, D2, and alpha. Of course, this algebraic formulation depends on the contact regime between the grains 1 and the grains 2. And this is another way to relate. So it is possible to exhibit a relation between the increment of the geometrical configuration parameters here and the deformation, the incremental strain at the macroscopic scale, which is imposed to the hexagon. For a very, very simple case here, the expressions are quite long, and I made a lot of error. I'm too old, maybe. And it is possible also by the derivation of the incremental mesoscopic stress to access.
A simple step and you go to Levi-Civita notation. You did 95% of work.
Yes.
Then like K-I-J equal.
Yeah.
No?
Maybe. So it is possible to exhibit the tangent stiffness matrix relating the incremental mesoscopic stress and the mesoscopic incremental strain. There is another term which is almost zero. This is a very small term, a correction term. When from one step to another, there is a transition regime between elastic and plastic regime. So once we have the expression of the tangent stiffness matrix, all the analysis in terms of second order work is possible. And as recalled by Felix Darl, this is the symmetric part of the stiffness matrix which is determinant in that purpose. And in 2D, the necessary condition for bifurcation can be written in terms of spectral properties of KS, which is that the minimum eigenvalues of KS must be negative. And of course, if the trace of KS is positive, the negativity of the second order work becomes dead KS negative. So once we did that, it is possible to determine the bifurcation domain defined by all the states giving negative eigenvalues. And we performed it on the case of the possible states achieved by the hexagon. And in elastic regime, the rainbow part is the bifurcation domain, and the grayscale one is the unconditionally stable state. And in elastic regime, we see that there is a poor dependence about the microstructure, and the condition for instability can be expressed very simply in the terms of interpenetration and elastic stiffness ratio between the grains 1 and grains 2. In elastic regime, however, the bifurcation domain is the set of all possible states. That means that the bifurcation domain is equal to the whole possible states achieved by the hexagon. So the use of bifurcation domain concept is not operative, and we introduce a concept of unstable states domain by choosing one direction of solicitation of loading, theta epsilon here, and calculating the second order work for this direction of loading. It can be shown that it is a very simple relation. The second order work, the expression of the second order work is very simple. So here it is possible to determine the unstable states for a given direction. Here, dealing with the soil liquefaction, we chose the strain increment ratio equal to -1, which corresponds to the isochoric deformation in 2D. And we find that the unstable states are the rainbow part of the possible states domain, and here the state is stable, and here the second order work is positive here, and it is negative on this here on the rainbow part. It is worth mentioning that the unstable domains are a domain is independent of the control conditions. The only assumption is that we choose a loading direction, theta epsilon, but it is dependent on the loading path. Because of course, if you choose another theta epsilon, you would have another unstable state, another set of unstable states. And it is also to be mentioned that under stress control loading, the boundaries between the stable, the positive second order work and negative second order work domains evolves because the directions of loading theta epsilon is not fixed if you control it under stress or mixed loading. So the partial conclusions on the theoretical study is that the state of the granular assembly needs stress and microstructure description to be intrinsically defined. Otherwise, for example, in this case, you see that the negative second order work is highly dependent on the microstructure here, alpha. The hexagon can be unstable, and elementary hexagonal pattern naturally takes into account the initial microstructure anisotropy, the directional character of the behavior of granular materials, and the hardening phenomenon due to microstructural evolution. So it contains all the good ingredients for the modeling of instability in granular media. So,
you have to
5 minutes.
You have to stop because you have taken 20 minutes.
It was not 25.
Yeah, if we want to have 5 minutes for the discussion. 2 minutes.
No, it was just here. There is a study of the distribution of hexagon because we only study one hexagon, and if we distribute the whole hexagon, the hexagon in the different orientation, then it is possible to exhibit some response of soil close to what is seen in experiments. For example, if we consider an isotropic distribution of hexagon, there are hexagons in all the directions isotropically, and an anisotropy distribution of the initial opening angles. So the opening the lengths of the hexagon are different depending on the orientation. Then it is possible to model either a completely dilative behavior or limited liquefaction behavior and complete liquefaction behavior. It is possible to show diagrams, etc., to study the liquefaction. Okay, so our concluding remarks is that it is possible to model the wide range of soil behavior types observed experimentally by just changing the microstructural parameters. And the development of micro-directional models opens the possibility to take into account the crucial effect of microstructure anisotropy in constitutive models. And the perspectives are to study the distribution of hexagon and to implement this model into a FLAC model to perform numerical simulations at the structure scale. Thank you.
Guillaume, I'm sorry to...
No, pas de problème.
Sorry to okay, so we have time for questions. Yeah, yes, next.
You described an elastic bifurcation criterion. What was the V1 there?
V1 is the branch vector between the... Between the grain 1 and the grain 2.
You can show the criterion once again.
Where is it? Here. In fact,
D1 is, let's say,
the length of the branch vector.
that ratio on the left is 1.
For example, when it's not loaded, it's 1. So if kt equals 0, it is possible to diverge. It is unstable, but if you increase the kt, which is the tangential stiffness, then you have to reach a certain amount, a certain interpenetration ratio to trigger the instability.
So is this the instability?
Yeah.
So it doesn't help.
Yes, we showed that under some loading, for constant confining loading, for very high stress, it is possible to reach this condition and to trigger instability under an elastic regime. The instability is is caused by the geometric, the microstructure evolution, which renders the symmetric part of the tangent stiffness matrix negative.
If you like the scientific debate, there is a scientific debate there. And I don't know if you have grasped exactly what is the idea behind it. But the idea is that basic idea is that you can have instability even though you have the elastic regime. So you are going to say it's possible from a thermodynamic point of view. I will answer. Yes, it is possible.
Larger than Kn is negative oscillation.
Sir?
If you have Kt larger than Kn,
Yeah.
you have negative oscillation.
Yeah, but it's not necessarily to consider this situation improbable situation or very rare situation. Just take the case where Kt equals Kn. Then this situation may arise, and then in this case you may have instability, or the other situation is when Kt is very small with respect to Kn, and in this situation you may have instability very easy, even though you are elastic. In fact, why we may have instability when we are elastic? Just because this is hypoelasticity. We have a hypoelastic model, not an elastic model, but a hypoelastic model. This is the key point. And this is what this is the key point hidden behind the equation. It is not an elastic or a hyperelastic model. This is a hypoelastic model. And this is why we may have a bifurcation domain. This is why the stiffness matrix is not symmetric, but it's no longer symmetric. And as Felix has shown this morning, because the key is not symmetric, we have a S part different from key, and in this condition, we may have bifurcation domain. Okay? If we were hyperelastic, then Ks equal to E, and the question of the bifurcation domain fell down. But in this case, we have the question of the bifurcation.
Generally, if we model real soils, the interpenetration is very small, so we do not have these elastic bifurcations.
You have two microstructural parameters, the orientation of the hexagon and the opening angle
Yes.
of each hexagon.
Yeah.
During the loading part, is there any correlation between the two? That is to say, is the opening angle reducing in the compression direction?
Yeah, totally.
Opening
Totally.
in the
Totally, because due to the kinematic assumption of proportionality of the deformation at the mesoscale and the deformation at the macroscale, this is naturally taken into account.
it is an hypothesis.
As I said here,
From the boundary condition.
Yes, the phenomenological model is replaced by the micromechanical model plus this assumption. And this is the key issue.